సుబ్రహ్మణ్య గారు సార్కి యాక్సెస్ ఇచ్చారా చూడండి ఒకసారి. సార్ లైవ్ లోకి రాగానే స్టార్ట్ చేసేయండి సార్.
ఓకే సార్. ఓకే
వచ్చేసారు సార్. సార్ కూడా రెడీగానే ఉన్నారు.
బట్
రెడీ సార్, అంతా ఓకే సార్.
సార్ గుడ్ మార్నింగ్ సార్.
మార్నింగ్
సార్. గుడ్ మార్నింగ్ సార్.
Very nice to start the program, please.
Okay sir. So good morning to all. So on the behalf of Department of Physics and Electronics, Government College Autonomous, so I welcome you to all to the National Webinar on Sustainable Photovoltaic Devices for Future World. So as a part of celebrations of Science Day, Department of Physics started conducting the online national webinar on sustainable photovoltaic devices for future world. So actually today this program will be delivered by two keynote speakers. One is from Dr. D. Sanjeev Kumar sir, Assistant Professor, Government College Autonomous Rajahmundry, and second speaker is from Dr. Anil Kumar Chauhan, Scientific Officer G, Technical Physics Division, Baba Atomic Research Center, Mumbai. So in this regard, I kindly request the president of the today's event and also the visionary person, Dr. David Kumar Swami sir, and also the sir is also currently acting as joint director to the Commissioner of Collegiate Education and also the Principal, Government College Autonomous Rajahmundry. Sir, I kindly inviting to give a inaugural remarks to the today webinar on this photovoltaic applications for the future world. Welcome you sir to give a
okay. Good morning
to the today's session, sir.
Yeah. Good morning everyone. Welcome all the participants and faculty members to this national webinar. So in view of this, on the eve of this conducting a series of webinars, National Science Day celebrations, that is to be held on 28th February, that is tomorrow. So I really appreciate the team and the head of the department and faculty members and the students of Government College Rajahmundry, Autonomous Institution, for this webinar. And then I really see that the efforts made by the HOD, Dr. Vishweshwar Rao and his team members are making possible for organizing this kind of webinars in the interest of student community. And also today's resource persons, Dr. Chauhan Anil Kumar from BARC and Assistant Professor Dr. Sanjeev from Government College Rajahmundry. I also welcome them. And then so the topic of this is, I think it is a sustainable photovoltaic devices for future world. So Government College Rajahmundry is working towards the student community for the last 1.5 centuries with many more innovative activities. So this is a department wherein the Department of Physics is playing a very important role and big role, the entire institution towards teaching, learning and research. So I appreciate the team should continue this, sustain this, and because the people will come and go, but the the efforts made by our predecessors shall be sustainable, shall be sustained, and in the interest of the student community. So I request once again the Department of Physics for their efforts to continue, and at the same time organizing these kind of webinars or seminars. So we'll certainly will gain knowledge and awareness towards certain topics that we have chosen. Because the Science Day celebrations is mainly pertaining to the physics department. But nowadays, everybody is celebrating, all of the science departments are also celebrating, because the science and technology has entered into the all fields of science, including social sciences. So I wish all the best, and I look at all the proceedings of this webinar will go in a smooth manner. It will be beneficial to the student community. So once again, I congratulate the entire organizing team for making this possible. Thank you.
Thank you, sir, for your opening remarks and for your suggestions. So we will continue. So in our vision that what you are expecting from Department of Physics. Thank you, sir. Thank you very much once again. So now I am requesting Dr. T.K. Visweswara, sir, the head of the Department of Physics, to give a introductory remarks for this today's session. So please take over.
Thank you, Gauri Naidu, sir. Respected President of this national webinar, Dr. David Kumar Rapaka, and Vice President, Sri K. Anjaneyal Garu, resource persons of this occasion, Dr. Anil Kumar Chauhan, Scientist G, Physics Division from Baba Atomic Research Center, Mumbai, Dr. Sanjeev Kumar, Assistant Professor, Government College, Autonomous, Rajahmundry, Co-Convener, Sri PVS Satyaji Garu, and organizing committee members and my dear participants, good morning to one and all. It's my privilege to speak a few words in this national webinar on sustainable photovoltaic devices for future world. The Government College Autonomous established in the year 1983 and the Department of Physics is established in the year 1930. PG courses introduced in the year 1970. This department has 24 sanctioned teaching posts and working with 7 PhDs. This is the second biggest department in this college and a biggest department in physics in the entire AP, offering 7 programs in UG and 1 program in PG. Nearly 1100 students studying with the physics background, and we have 2 research labs, namely crystal growth and nanotechnology labs. The department has very big laboratories and a departmental library and 1 antique lab, which is equipped with 150 years old equipment. Most of them are made in London. The Department of Physics so far conducted many workshops, seminars, summer research projects, orientation programs on national and international levels. So far, the department produced 2 MPhil and 10 PhDs. This department has MOU with the prestigious organizations like BARC, RRCAT, University of Lowell, USA, etc. Our principal is also Joint Director of CCE AP, encouraging our departments in all aspects. We must be thankful to our Commissioner, sir, for giving permission to conduct this webinar on online platform. Also thankful to the authorities of BARC for their valuable support. Tomorrow, that is on eve of Science Day, all the science departments of our college are going to observe the National Science Day with the theme An Integrated Approach in Science and Technology for a Sustainable Future. All the science departments of our college conducting student competitions. As a part of that, the Department of Physics conducted a quiz program. In this program, 1225 students were participated. The Department of Physics maintained 3 best practices by name Lab to School, Know Your Scientist. It is a daily student activity, and giving joy to the weaker sessions. I hope this webinar will provide knowledge among the science levels. Thanking you to all. Now I hand over mic to Sri Gauri Naidu. Thank you.
Thank you, sir, for your opening remarks and also a brief introduction about the Department of Physics and what kind of like research activities and teaching activities and all the kind of things what supposed to be taking place in this in this department. And thank you very much for your remarks. So now I am requesting co-convener of this today program and head of the Department of Electrons, Sri P.V. Sachaji sir, Government College Autonomous, Rajahmundry, to give an introduction remarks regarding the today's program. So I am handing this to Sri P.V. Sachaji sir.
Honorable Joint Director Dr. David Kumar sir, President and Principal of this college, HOD Head of the Department of Physics Dr. T.K. Visweswarrao Garu, and other organizing committee members, the participants, a very good morning to one and all. Actually, as a traditional physics is defined in considering the 2 points. One is it is a branch of physics, branch of science, which deals with the properties of matter and energy. And moreover, energy can either be created or destroyed. Unfortunately, we are losing the energy resources nowadays day by day. And moreover, based on this Science Day celebrations, this year theme is sustainable photovoltaic devices for future world. So alternatively, we have to strengthen the natural resources or converting the energies available natural resources. Based on this concept, the Department of Physics and Electronics is to organize 2 webinar programs. Yesterday itself one is over, and today is by with the 2 speakers, 2 resource persons. One is Dr. D. Sanjeev Kumar sir on the topic Introduction to Photovoltaic Devices, and another is Dr. Anil Kumar Chauhan sir on the topic Photovoltaic devices, which are useful to alternate the naturally available resources to the utilizing property. And I'm sure that definitely this will ignite the young minds, researchers and students and etc. And therefore, from the Department of Physics and Electronics, I once again wish you welcoming these 2 persons. Sir. Thank you very much for this opportunity. Welcome, sir.
Thank you, sir, for your introductory remarks regarding this today webinar.
And also welcome to Dr. Sri A. Anjaneyulu, sir, Vice Principal of this college. Introduction remarks.
So as a part of this national webinar on sustainable photovoltaic devices for future world, today we'll be having 2 keynote lectures from 2 resource persons. One is Dr. D. Sanjeev Kumar sir, Assistant Professor, Government College Autonomous, Rajahmundry, and second one is Dr. Anil Kumar Chauhan sir, Scientific Officer G, Technical Physics Division, Baba Atomic Research Center, Mumbai. So in this regard, I would like to invite Sri K. Venkateswara sir to give a brief introduction about Dr. D. Sanjeev Kumar sir. Sir, please introductory about Sanjeev sir.
Sir, am I audible, sir?
Yes, sir, you are audible.
Sir, good morning, one and all. I am privileged to introduce to you Dr. D. Sanjeev Kumar, Assistant Professor in Physics, resource person for session. I am happy to say he is an alumnus of this college. He is an alumnus of this college. He has finished his master's degree from this college in the year 2005. Okay, now? Later, He did his MTech and PhD from University of Hyderabad. There he worked on spin-orbit interaction in quantum dots. In 2018, he was selected as lecturer in physics from APPSC through APPSC and posted to this college. He published 8 papers in international journals and 6 conference proceedings. And at present, he is guiding 2 scholars for their PhD program. He published a book on solar energy, a skill course offered by APSA for UG programs. He is one of the authors of the first year PG UG textbook, Mechanics and Oscillations. At present, he is teaching for both UG and PG programs in this college. With these few words, I invite Dr. D. Sanjeev Kumar to deliver his lecture. Thank you.
Thank you, sir. Thank you very much. So with this, I'll start my lecture. Screen sharing. So you need to enable the screen sharing, sir.
Sir,
Screen sharing need to be enabled, sir. Need to enable the screen sharing.
ఒక్క నిమిషం సార్ అవుతుంది.
సార్ అందరినీ మ్యూట్ చేయండి సార్.
Okay. Now I got.
స్క్రీన్ షేరింగ్ ఇప్పుడు ట్రై చేయండి సార్.
Yes, sir. So is my screen visible, sir?
You are sharing, right, sir? Right, thank you, sir.
Okay, sir. Thank you. So thank you all, and I'm going to start my presentation. So my talk will be divided into 2 parts. In part 1, we'll be discussing about right. So in the first part, I'll be discussing about photoelectric effect and photovoltaic effect differences. Materials required for
dear participants, sir, please be, sir, 1 minute, sir.
Yeah.
Sanjay, sir.
Okay, sir.
Dear participants, please be in mute. Okay, so some of the your participants are coming to in between the lecture, so that it will be so disturbed. Okay, kindly requesting all the participants, please be mute your mic. Okay, so unless there is an interruption to the lecture. Okay, thank you.
Right. Thank you, sir. So in the first part, I'll be discussing about photoelectric effect and photovoltaic effect differences, and various materials that are going to use for fabrication of solar cells, and especially my main focus will be on semiconductor type solar cells, their fabrication, construction details, and their working principle. All those things I'll be discussing in the first part. And in the second part, I'm going to deal with sustainable energy sources, classification of various types of energy sources, and various terminologies that deal with sustainable energy resources, and scenario of solar PV systems and the classification of various types of solar PV cells. So coming to the first part, photovoltaic effect and photoelectric effect. So the major difference between photovoltaic and photoelectric effect is this. In photovoltaic effect, light will generate charge carriers, positive and negative charge carriers in the material, and the charge carriers cannot come out of the material. They will be separated or detached from their atoms, but they will be within the material. Whereas in photoelectric effect, the electrons or whatever charge carriers will be ejected out of the material. So in both the process, light mobilizes the electrons, but in photovoltaic effect, the electrons will be within the material, and in photoelectric effect, electrons will be ejected out of the material. So in the periodic table, what are all the elements that we can use to develop these solar cells or photoelectric cells is a matter of interest. As we know, these first group elements, lithium, sodium, potassium, rubidium, all these elements have one electron excess compared to their stable configuration. So they are ready to give up that extra electron, and they try to be stable. So from those atoms, we can easily remove the electron and get some photoelectric effect. So this is the first kind of photoelectric cell that was developed, where the emitter is a metal plate coated with sodium or any kind of first group elements, which can give up electrons very easily. When light incidents on those materials, electrons will be ejected, and there is a collector with which is connected to a positive terminal of the battery, and emitted electrons will be collected by this metal plate or metal bar. So in photoelectric cells, we require a battery to collect the generated electrons. Without that, emitted electrons will be simply within the chamber, but we can't use them. But this photo cell cannot be used as a power source, because we require an external source to collect the electrons. So whereas in photovoltaic effect, we have a different scenario. Electrons will be emitting out of the electrons and holes will get separated from the source atom, and they'll be moving freely within the material. So we can use them for other purposes. So what other elements can be used to develop these photoelectric cells, photovoltaic cells, is a matter of interest. And out of this, I majorly focus on semiconductors. So before going to that, I'll be discussing about formation of bands, or how individual atoms Okay, am I audible? Okay, thank you. Right. So even if we take a single atom or group of atoms, in this graph we can see only energy levels as long as the atoms are non-interacting. And when the atoms start interacting and form bonds, there will be a redistribution of energy. So the single line here now contains 100 or 1000 atoms. And when the bond formation process starts, there will be a redistribution of energy. Some of the atoms will gain energy and some of the atoms will lose energy. So there will be a shift from the mean position. So all we can see in this graph is a band of energies. So some atoms gain energy and some atoms lose energy, and in total we'll see bands instead of lines. So this is the actual scenario when we go from energy levels to energy bands. There will be redistribution of energy, and at some point we can even have valence band and conduction band get overlap, and at some points we can have a gap between valence band and conduction band, and at some separation between, I mean here on x-axis I'm taking the separation between the two atoms. So if I bring two atoms together, at certain separation the atoms still remain as atoms and we see energy levels, and at certain level of separation the atoms overlap, their energy levels are overlap, and we see bands. Even in the bands, valence band and conduction band get overlap. And if we go further and further, lower separations, the band gap increases. So based on these atomic level separations, we can classify the materials into three types: conductors, insulators, and semiconductors. So in insulators, band gaps are very high. In semiconductors, band gaps are of the order of 1 electron volt to 2-3 electron volts. Here it is more than 10 electron volts. And in conductors, there is no band gap. Valence band, conduction band get overlap. So now coming to semiconductors. So semiconductors are the fourth group elements in the periodic table. So all they have is 4 electrons in their valence band, and they require 4 more electrons to get the octet configuration or a stable configuration. So to get stability, they can't gain all the 4 electrons, or they can't give up all the 4 electrons. So what they do is they share the electrons, so that each atom can now see 8 electrons around itself in the outermost shell. So thus each atom gets stabilized by sharing electrons. So this process is called covalent bonding, and then the valence shell of each atom we can see 8 electrons. Thus they get stabilized, and we can break the bond and take the electrons to next level, next energy level. That means we are raising the energy of the electrons so that they can go from valence band to conduction band by crossing the energy gap. So if we supply sufficient amount of energy, the bonded electrons will detach from the bond and reach to conduction band, and they leave back a hole in the valence band. So remember that absence of electron in a bond is called hole. Only bonded electrons will leave holes behind. Now electron current and hole current. So in the conduction band, electrons will move smoothly, freely, whereas to move a hole in the valence band, we require to break a bond and create a new bond. So if the hole has to move from one end to other end, we need to break a bond in the next level and bring the electron from this location to this location, so that actually electron is moving backwards, and we feel it as if the hole is moving forward. So that's how the whole current requires breaking of a bond and creation of a new bond, and this is a slow process and it involves a lot of energy. So coming to solar cells, so we prefer electron current more compared to hole current, because whole current generation requires a lot of energy, because we have to break a bond and create a bond. It requires a lot of energy, whereas moving an electron within the material requires less energy compared to holes. So in other words, we can tell the same statement in a different language by saying that the effective mass of hole is high. Means I require more energy to push the hole from one end to other end. So I call it as effective mass of the hole is high compared to effective mass of electron. So now next one is the Fermi level. So when we are not giving any energy, all the electrons are bonded electrons, and their energy will be up to the level of valence band. But due to uncertainty, the energy may rise a little higher to a little higher values. So the valence electrons can be seen even at a little higher energies. So that maximum level an electron can go even at 0 kelvins. I mean, without giving an energy, that energy level is called Fermi level. So this is the Fermi level for intrinsic semiconductor or a pure semiconductor. It lies in between valence band and conduction band. And if we rise the temperature, I mean, this I'm defining at 0 kelvins. If I rise the temperature, electrons can go to little higher levels, so that my definition of Fermi level shifts to little higher levels. So the Fermi level lies exactly in between valence band and conduction band at 0 Kelvin, and with rise in temperature, this shifts up. So this is very important while designing Pn junctions. The Fermi level makes a difference. So now coming to extrinsic semiconductors, when I dope with a pentavalent impurity, what happens is there is an excess electron which is not participating in the bonding. So I can easily move it to conduction band. So in the energy level diagram, I can show those electrons little nearer to conduction band, so that with a little energy, I can shift these electrons into conduction band. So now the Fermi level lies in between this donor level and the conduction band. So in N-type semiconductors, the Fermi level shifts upwards. And in P-type semiconductors, there is a absence of electron. There are trivalent impurities added instead of the semiconducting atom. So there is a hole, and this whole energy level will be little nearer to valence band. And with a little supply of energy, we can shift this hole into valence band, because hole moves in valence band. So with the little supply of energy, the hole enters into valence band. So now the Fermi level lies in between the acceptor level and the Fermi level. So the Fermi level, I mean valence band edge. So the Fermi level shifts downwards in the case of P-type semiconductors. Now coming to the formation of Pn junction. When I join a P-type material and an N-type material, N-type semiconducting material, here I'm showing the atoms that I have doped. So in N-type material, there will be excess electrons and a positive charge in the nucleus. And in P-type material, there are excess holes and negative charge within the atom. So in the N-type material, so in the P-type material, there will be excess holes. There are holes. I'm depicting them by positive sign, and there is a negative charge sufficient for the balancing of the charges. So when I join this P-type material and N-type material, so here I'm showing all the doped atoms only. I'm not showing the semiconducting atoms. I'm showing only the doped atoms. So when I join this P-type material and N-type material, what happens here is the negative charges on the P side will repel the electrons on the N side. So the electrons at the junction will be flushed into the N region. Okay. So the electrons at the N region junction will be flushed into N region, and the holes on the P side will be repelled by the positive ions on the N side. So the holes will be flushed into P region. So there will be a depletion region, means charge, no movable charges will exist at the junction, and there are only positive ions on the N side and negative immovable charges on the P side. So there will be an electrostatic force of attraction between these two, and they form a bonding, and that's called a Pn junction. So now, depending on the doping level, if we dope more and more number of atoms, what happens here is we can have more number of ions available within a single layer. If the doping level is very low, we can see only less number of atoms or ions at the junction at one level. So there are, let's say in this diagram, I can see 4 ions in the first layer and 4 ions in the second layer, in total 8 ions. Whereas if I increase the doping level, what happens is I can see all the 8, nearly 8 ions within the first layer itself. So if I increase the doping level, what happens is the depletion region width reduces. So this is also one important parameter that decides the properties of solar cell. If I raise the doping level, the depletion region width reduces, because I can get more ions readily available within a single layer. So now, with all this information we have developed till now, I'm going to construct a solar cell. So here I'm taking a metal plate or a substrate. On the metal plate, I'm depositing the P-type material, P-type silicon material, and over that I'm depositing N-type silicon material with heavy doping, N plus. I'm representing it as N plus. So here there is a heavy doping. So the effect is on N side depletion region width is very low, and on P side depletion region width is very high. And I'm ensuring this the width of N-type material also very small. So you can see that P-type entire material width is very high and N-type material width is very low. And over that, I'm coating an anti-reflection material, so that whatever light falls on the material will be directly entered into the solar cell. So with this anti-reflecting coating, I'm ensuring no light escapes out of the solar panel or solar cell. And the generation, the electron hole generation part is at the junction. So I have to ensure the light should reach the junction. So that is why I'm taking very thin N-type material, So this N-type material is very thin. But if I take very thin material, I can't have more number of carriers. That is why I'm taking N plus, heavily doped material. So within this small region also, I can have more number of carriers available. And I'm deliberately choosing electrons because I can move them or mobilize them with less amount of energy. So I'm keeping N-type material on the top. I'm keeping its thickness very low. And I'm doping it heavily so that I can avail more number of carriers readily within this small thickness material. So now what happens? At the junction on the N side, we have positive ions, and on the P side, we have negative ions. And when the sunlight falls at the junction, or when the sunlight reaches the junction, intrinsic material bonds are broken and they generate electron and hole pairs. In the intrinsic material, bonds are broken and we can see electron hole pairs. So what happens? The ions at the junction, the negative ions at the junction will repel the electrons, and the positive ions at the junction will repel the hole downwards. So the holes will be moved downwards and electrons will be moved upwards. And if we connect a wire, the electrons will be free to move through the wire and reach the other end. So in the process, the energy gained by this solar energy will be transferred to the bulb or whatever device we connect at the other end. So this is what happens in a solar cell. So the magic elements are this. If we have more dopants, if we heavily dope the N-type material, we can have more number of electrons or more current. And if we maintain very low thickness for N-type material, we can have more sunlight reach the depletion region. So these are the control elements for this solar cell. But there is a rule called law of mass action where we cannot control, we cannot infinitely dope the material. So the limit is equal to the number of carriers. So here it is, second. Sorry for the inconvenience. So the law of mass action says this. Is my screen visible? Okay. So number of holes in a extrinsic semiconductor and number of electrons in extrinsic semiconductor, the product of these two will be equal to number of electron hole pairs in a intrinsic semiconductor. So we can't raise this number of holes or number of electrons infinitely. So it also has a limit, so we can't infinitely dope a material. That is the limitation for the solar cell. Next is the electrons, whatever lifted up N-type material edge, should remain there forever. They should not get absorbed within the material. they should wait at the surface of the n-type material till we use them. At this same time, the holes on the p-side material should remain there forever till we use them. Otherwise, all our effort will go waste. So we need to have a mechanism to retain the electrons or without being them recombined. So what are the mechanisms? One possibility is this, choosing a proper kind of band gap. So there is a this valence band and conduction band that we have seen as a flat bars is actually is not a flat line. It is a zigzag line as shown here. So the valence band is a zigzag line and the conduction band is also a zigzag line. So the band gap now can be defined in two ways. One is direct band gap and indirect band gap. In this picture, the shortest distance between valence band edge and conduction band edge is not straightforward. It requires a horizontal shift also. This is the shortest distance, but valence band edge, top of valence band and bottom portion of conduction band are not on a same straight line, same vertical line. So this is called indirect band gap. So there are two kinds of semiconductor materials. One with direct band gap, where the valence band edge and conduction band edge stay at the same location, same vertical point. And indirect band gap semiconductors, valence band edge and conduction band edge are shifted by a small energy. So here on x-axis, we are considering momentum of the particles. So in direct band gap semiconductors, we don't need to supply any additional momentum to the electrons. Whereas in indirect band gap semiconductors, we need to supply additional momentum to the electrons. So what happens? So here, this kind of transitions, a light also can do. Light can do this very easily. Whereas in indirect band gap semiconductors, we need to supply momentum also to the electrons. This light cannot do. We require thermal energy also. So for this purpose, for direct transitions, we can use light. Whereas for indirect transitions, we require light and thermal energy. So we choose this kind of materials for solar cell fabrication. And these are the kind of materials we choose for LED fabrication, because when we give energy, the electrons will rise to next level, and when the electron comes back, it gives out the light. Whereas in this case, in indirect band gap semiconductors, we require light energy as well as thermal energy to rise the electron, and for the electron to come back, it has to give back the light energy as well as the thermal energy also to come back. So as long as the thermal energy exists, or as long as the sun focuses on the solar panel or solar cell, the electron will never come back. So it stays there till we use them or till we pass on them to a charger or a bulb or any device. So we choose this kind of materials with indirect band gap for solar cell fabrication. So silicon with 4 valence electrons is an indirect band gap semiconductor, and we use them for solar cell fabrication. All 4th group elements, silicon, germanium, all these things are used as solar cell materials. And in the second case, we can use a 3rd group element and a 5th group element in combination to get octet configuration. Examples, gallium arsenide, or we can use aluminum arsenide or aluminum phosphide. Whatever the dopants can be directly used to prepare the semiconductor material, complete semiconductor material. So this combination, a 3rd group element and a 5th group element combination, also acts as a semiconducting material, but they have direct band gap. So we can use them for LED manufacturing. Okay, so for solar cell manufacturing, we are choosing 4th group elements, silicon and germanium. Another kind of issue is we can use even 3-5 group semiconductors also, but here we see the here we see the energy level diagrams for Pn junction formation. Okay, so I'm looking for Pn junction formation and energy level diagram for Pn junction. So here the Fermi level in p-type material is nearer to valence band, and Fermi level on an n-type material is nearer to conduction band. And as we already know, the Fermi level is the maximum energy level an electron can reach. So on p-type material, electron reaches up to valence band edge and a little higher, and on n-type material, electron reaches little higher. So when we combine these two, what happens? Means it is equivalent to combining 2 water tanks with 2 different water levels. So what happens is the level balances, energy levels balance. So on one side, electrons reach up to certain level, and on the other side, electron reaches to little higher level. So when we join these two, these energy levels balance. And we have Anderson rules to draw this energy band diagram. So what we have to do is we have to match the Fermi levels and then draw downward and upward curves to join the both side materials. So here I'm matching the Fermi level. A p side Fermi level is matched with n side Fermi level, and now I have to join drop down the p side energy levels, and I have to rise the n side energy levels, so that at the end I can see a Pn junction energy level diagram like this. So here what we did is we have matched the energy levels and then drop the n side p side energy levels and rise the n side energy levels, so that they are smoothly joined together. So these simple rules, they look very simple, but when we come to little complex systems, the rules make a magic that we see here. So here I'm joining 2 semiconductors with different band gaps. So on p side I have a very low band gap, and on n side I have a very high band gap. Now I am applying the same rules. I have matched the Fermi levels, and on p side I have to drop down the energy levels, and on n side I have to rise the energy levels. So what happens here is there comes a trap. So now the electrons can be trapped here in the conduction band. So these kind of traps are used for LED materials, but for solar cells, these kind of traps are damaging because they stop the electron flow, or they can also be used for storing the electrons. I mean, both possibilities are there. We can hold the electrons so that they can recombine easily, or they can get destroyed easily, or the material can hold these electrons in these traps. These are the 2 possibilities. With this, I'm going into the recombination types, and what I mean by that is what are the possible ways that electron dies within the material before we use it for any purpose. So when sunlight falls on the material, the electrons will be rise to conduction band, but they can't stay there forever for longer times because of so many reasons. One reason is radiative recombination. Because So here the electron can come back to the valence band without giving back thermal energy. So it will be directly shifting to valence band. So in that case, it doesn't need to give back the thermal energy, so it can directly come back to ground state. So that we cannot control, even the sunlight cannot control it. So that with that possibility, electron comes back to ground state. Means what I mean by that is, if the electron rises to a different level, let's say, if we give only this much energy, electron will reach here. Let's say, suppose this is 1 electron volt. If I give 1.4 electron volts, what happens? It reaches directly to this level, straight away to this level, and this can freely come back. It doesn't need to give back the thermal energy because it did not take any thermal energy. Just by taking light energy, it reached the conduction band. So it can come back readily, very easily. So that kind of transition we cannot control. So that is one possibility, radiative recombination. Another possibility is traps that we have seen already. When there are traps, electrons will accumulate over there and they can come back to valence band or ground state easily. Another possibility is defects. When there are defects, electron doesn't need to travel all the way to combine with the hole. It can travel up to this defect, and then a hole also come back to that level. And they can recombine very easily. So that that is one possibility. And another possibility is Augur recombination. Augur recombination is electron will come back to ground state, releasing a photon, and that photon will be absorbed by another electron. So we don't have an electron. Suppose we have 2 electrons in the conduction band. What happens here is, one electron is falling back to ground state, giving out a photon. So if that photon is utilized to break another bond, then we can have an electron available in the conduction band, but that is not utilized for that purpose. If the released photon is utilized to rise an electron within the conduction band, then all we have is only 1 electron. So we are losing 1 electron within the conduction band. So initially we have 2 electrons in the conduction band. One electron falls to ground state, releasing a photon. If that photon is utilized to break a bond and create a new electron hole pair, that is okay. But if that is not the case, if the electron is utilized, if the photon release is utilized to rise an electron within the conduction band itself, then all we have is only a single electron in the conduction band. That's how electron count reduces. Another possibility is donor-acceptor pairs. If we have a donor and an acceptor as a pair, they emit a photon, and the emitted photon will be readily absorbed by another pair. So the process continues, and all we have is only 1 electron available in the conduction band. So with all these processes, we have electrons recombined, or we lose electrons without being used. So we have to choose the proper material and proper design, proper structure for the material also to avoid all these recombinations for proper working of solar cell. And so with that, I'm going to next part. So as of now, we have discussed about semiconductor type solar cells. What is the working mechanism? What is the construction details? And what are the drawbacks or whatever recombination methods that reduce the energy produced by semiconductor solar cells. So then I go to next level with a minute break.
So good morning to all. Due to some technical reasons, like power grid failure from the BRC end, so that is the reason Dr. Anil Kumar Chauhan sir is not supposed to be deliver his lecture. So that what will be.
Let me tell you, he is no. The power is restored.
Okay.
Somebody can contact him.
Okay,
Okay.
sir.
So somebody can contact him and confirm that power is restored. Then you can schedule his talk.
Okay,
he is
sir.
ready.
Okay. Now, sir is ready, sir.
Hello, good morning to all of you. I am A.K. Chauhan. Now the power is restored in the Mumbai. So I'm just now I have joined.
Okay, sir.
So
Thank
what
you,
is
sir.
the status actually?
Thank you, sir. In next 10 minutes, I'll finish my talk and you may
Okay. Sure.
join. Thank you,
I'm
sir.
actually trying to arrange this internet because there's some issue with that. So it will take 5-10 minutes. No problem. 10 minutes are fine.
Okay, sir. Thank you, sir.
Thank
We
you,
will get back to you within 10 minutes, sir.
Sure,
So then
sure.
you can get ready, sir.
Sure.
Okay, sir. Thank you very much for joining. Okay.
Thank you.
So Sanjay sir, you can continue. So
Sanjay sir, please continue.
Yes, sir. Thank you, sir.
And
So,
you finish
coming
your
to-
class by at least 10 minutes
Yes, sir.
from now.
10
Bye.
minutes. I'll be. So coming to second part of this, my talk, classification of energy sources and sustainable energy resources. So these are the basic classification of various types of energy sources available. One is direct and indirect. I may call them as primary and secondary sources. So primary sources can be directly used, like coal can be used to heat water or whatever. Solar energy also can be directly used to heat materials. And whereas for other things like electricity, steam energy cannot be used directly. I mean, the resources can be converted to electricity. I mean, we require some other resources to generate these energy sources, and these energy sources like electricity can be used further. So these are indirect energy sources. Electricity is an indirect energy source, whereas coal, natural gas, biomass all are direct or primary energy sources. Another classification is commercial and non-commercial energy sources. So they can be readily available. I mean, they can be connected. Non-commercial sources can be collected, like cow dung, firewood, agriculture waste, solar energy, thermal heaters. They can be directly collected from nature. Whereas petroleum, natural gas requires some processing, and we need to use, or we need to buy them. Another is conventional and non-conventional energy resources. So these are the hydrothermal energy or hydroelectricity. These are conventionally available for so long time. Whereas solar energy, wind energy, tidal energy sources, they are very new. So they are called as non-conventional energy resources. Another classification is renewable and non-renewable energy resources. So renewable energy resources, there are two definitions for renewable energy. The energy resources which cannot exhaust within human lifetime. I mean, within 100 years or 1000 years, they cannot exhaust. So solar energy, wind energy come under this category. So they will never terminate within a human lifetime. Whereas which can be regenerated again and again, those kind of energy resources also called renewable energy resources. Hydroelectricity, every year we have rains, and we can generate power from hydro energy. So they are renewable energies. Biofuels, so we can put the crop whenever we want, or in the season, and then once the crop is chopped down, we can regenerate, or we can cultivate them again. So these are the two possibilities, possible definitions of renewable energy. One, which will never end within a human lifetime. Another, which can be regenerated again and again. So this coal, natural gas cannot come under renewable energy. They're called non-renewable energy sources. Another is green energy. So here we need to know the definitions of carbon footprint, green footprint, and ecological footprint. These are very essential things to define further things. So carbon footprint is the total amount of greenhouse gases a fuel emits during its usage. So biofuel or hydroelectricity have very less carbon footprint during their usage, but during their production they have very high carbon footprint. So they cannot be considered as green fuels. Green footprint deals with both production time carbon releases and usage time carbon releases. So let's say we come to this biofuels. Biofuel cannot be considered as a green energy resource, because while we convert these biofuel plants into fuel, the conversion efficiency is at most 15%. The rest of the 85% waste need to be burned down. So it releases a lot of carbon and unnecessary gases into the environment. So it has a very large green footprint. So it cannot be considered, biofuel cannot be considered as a green fuel. Whereas biofuel can be considered as a clean energy because after generation of the fuel, it produces very less amount of carbon emissions compared to other fossil fuels like petrol and all. So we need to be very careful with these definitions. And ecological footprint deals with animals and plants also during production, after production. So production of this fuel, if produces any harm during production or during usage, then it will have very high ecological footprint. So we need to ensure whatever energy resource we have developed should have very less ecological footprint. That means it should not disturb the environment, or it should disturb the environment to a very minute level. That is called ecologically best fuel or sustained fuel source. So for example, hydroelectricity, while generation of hydroelectricity, there will be so many problems like algae and fungi will be accumulated in those waters. So they release methane gases, which is a greenhouse gas. So this macro hydroelectric plant cannot be considered as a sustainable energy source. So it is a clean energy. It cannot be considered as a sustainable energy source. And also the huge amount of water body produces a huge amount of water vapors, and it produces a temperature difference in the surrounding environments. And also at the bottom of the water layer will be at low temperatures that kills the fishes. That is a major problem. And also it stops the movement of migratory fishes across the dams. So for that purpose, we need to have an additional construction. It is called fish ladder, where fish can jump from one pond to another pond to reach the top level of the barrage. So even Polavaram, here in Andhra Pradesh, this Polavaram bridge construction was stopped by National Green Tribunal for 1 year, just because they did not construct the fish ladder. And very recently they have constructed the fish ladder, and now the downstream fishermen, I mean, actually that time fishermen have complained about the availability of fishes in the downstream because they could not find any fishes in the downstream because of the dam construction. And now the fish tank is, fish ladder is developed, and now Polavaram Dam downstream also have good number of fishes. So the best alternative for macro hydroelectric plants are the mini and micro hydroelectric plants, where we can construct these mini electric plant even on a agricultural canal. We can develop 1 megawatt power also from this, and we can have multiple such plants throughout the downstream. And micro hydroelectric plants, these can be developed even at a household, even within a single household can develop that. And coming to electric vehicles in India, the major problem using electric vehicles may not solve the problems, because the generation of electricity in India produces a lot of carbon, because 75% of the Indian electricity is from fossil fuels. So, I mean, even recent in 2021, 49% of the fuel generation is from fossil fuels. Electricity is from fossil fuels. So we cannot rely on electric vehicles completely. So even eco-friendly tableware, these are, I mean, nowadays we are using paper bags and all. These are not eco-friendly things, because the issue is to develop a single paper bag, we need to chop down so many plants and trees. Whereas if we use these kind of reusable bags, even if it is made up of plastic, it is eco-friendly because it is not harming more number of trees. So this kind of reusable plastic bag has less ecological footprint compared to a paper bag. So we should have very less ecological footprint compared to green footprint.
Sorry for the Sanjeev.
Yes, sir.
Could you please complete your
Yes.
talk within 2 minutes, please?
Yes, sir. Thank you, sir. So people are developing these pond cities where even within cities, groundwater level can be raised by developing various methods. And different types of solar cells, maybe our next speaker may discuss about other types of solar cells. Like this perovskite solar cells, organic solar cells, biohybrid solar cells and all. And environmental impacts of solar PV systems are they require very huge land area. A hydroelectric plant, mini hydroelectric plant requires 0.2 acres of land for 1 megawatt generation, whereas a solar plant requires 5 acres of land. And they require very huge water content, water cooling systems for concentrated solar cells. And they use toxic elements also. So those things our next speaker may discuss very deep in detail. And this is the solar energy scenario in India. Now only 3% of the energy requirements or energy production is from solar energy, and coal energy is 71%. That is why, I mean, we cannot rely on electric vehicles as of now within India. And now India is planning for green grid initiative, one sun, one world and one grid initiative, where solar energy also can be connected to grid directly, because grid requires a continuous power supply. So we cannot connect solar energy sources directly to grid, because when the solar energy shuts down in the evening, grid gets damaged. Whereas if worldwide all other countries also connected to the same grid, if one end of the world is in darkness, other end of the world will be generating solar power, so that at some point of the world, energy will be supplied to the grid always 24 hours. So that is the initiative started by India, and it is initiated in Glasgow. So these are the updates and details of sustainable energy. Thank you, sir. Thank you all. And any questions, sir?
So if anybody having questions, please you can ask to Dr. D. Sanjay Kumar sir. So otherwise, so thank you very much, sir. So for your very interesting talk on photovoltaic cells. Okay, in this regard, I am requesting Dr. B. Harnath Reddy sir to give a feedback about this talk, sir.
Okay, sir. Sir, am I audible? Yes, sir.
You are
Sir,
audible.
yes, sir. Sanjeev sir, thank you, sir, for your enlightening talk on photovoltaic devices, which is very useful to all of us. As we seen, entire the talk is very clear and easily understandable to all of us. Whatever we have seen, energy resources are losing day by day, and we need to look for alternative energy sources. This talk is entirely based on that one, under the material classification, energy bands formation, and selecting a material whose construction is very clearly discussed in entire the talk. So this is very useful to all of us, sir, which is we are seeing in our renewable energy labs also. So we hope we all enjoyed your talk, and thank you, sir, for your sharing your knowledge with us. Thank you.
Sir. Thank you. Thank you all.
Thank you, sir.
There is any questions or slide? Okay. Thank you all.
Thank you, sir.
A very pleasant good morning to all of you. I deem it a privilege to introduce Dr. Anil Kumar Chauhan, resource person of this session. Dr. A.K. Chauhan joined the Baba Atomic Research Center, Mumbai as research scientist in 1993 after completing a one-year postgraduate training program in physics from BARC Training School. He has completed his PhD in Science from Mumbai University and carried out his postdoctoral research work at Institute of Electronics, Microelectronic and Nanotechnology, University of Lille, France. He is presently working on the development of organic devices and has published more than 75 research articles in international peer-reviewed journals and has more than 100 conference presentations. He is the recipient of IFCPAR and DST JSPS fellowships for his research. At present, he is the head of Organic Devices section of Technical Physics Division in BARC. He is also professor in Physical Sciences at Homi Bhabha National Institute, Anushakti Nagar, Mumbai. He served as an editor of journal Material Science for Energy Technologies published by Elsewhere and guest editor for journal Bulletin of Materials Science published by Springer. Thank you.
Thank you, madam, for a nice introduction. I also would like to thank Professor Rao and other organizers for giving me an opportunity to speak on this occasion. Can I share my slide?
Yes, sir.
It's visible to all, sir.
It's visible?
Yes, sir.
Well, I'm not able to put it. Okay, fine. So, first of all, I again thank Professor Rao for inviting me, and of course other members who are organizers for this National Science Day celebrations at Government College. And I will be speaking on photovoltaic devices in general, because the talk is for the students. So I will confine myself to very basics of the photovoltaics, and I will try to cover all the things in the photovoltaic technologies as far as this technology is concerned. In the beginning, I will give a brief introduction about our center. So BARC is a multidisciplinary R&D organization. All of you know it. And whatever you say, kind of research that is going on in BARC. Start from, it is not only a research institute for reactor technology or nuclear science and engineering, but it covers almost all aspects of the research. That includes of basic sciences, material development, Newton X-ray beam lines, and whatever you can imagine, all the things are going on in BARC. It was established in 1954, though things started a bit earlier, and it has, you can see, about 14,000 employees, and out of them 4,400 are scientists and engineers. You can imagine it's a very huge, you can say, organization. And this is depending upon the, you can say, work culture or type of actual work. It has been further divided because it's such a big organization. It is very difficult to, you can say, control from a single place. So it has been divided in some groups. So there are 19 different groups. We belongs to physics group, where the research related to physics is going on. And then these groups are further divided into divisions. So in BARC at present, there are 94 different divisions, and each division has a specific and definite mandate which we are doing. As far as the say recruitment in BARC is concerned, we are adopting a very different approach, that is hire and train approach. So every year we you can say advertise. That advertisement has means just now, I think last month it has appeared. And then we there is an interview. First there is a written test, and then after the written test, then there is an interview. So if you clear both of them, you can get you can say selected. And after that, after this selection, this is a you can say training school approach. After this, we select from all branches, starting from physics, chemistry, biology, and all engineering branches. So typically a batch contains from 150 or 100 to 200 persons, sometimes even more, sometimes little less. And then for 1 year, they got a rigorous training on all aspects of research. And then they are absorbed in different divisions. So this is for the students who are MSc, they can apply here for this. Now, as far as our division is concerned, I am from Technical Physics Division, and the mandate of Technical Physics Division is development of materials, devices, and beamline for the physics research, basically. And actually, I am not able to remove these things. Not able to see full screen. I don't know why. So I'm from Organic Devices section, and the mandate of our section is to carry out research and development towards fabrication and characterization of low-cost organic devices. And these devices include organic solar cells, organic memory devices, organic thin film transistors, organic LEDs, organic thermoelectrics, all such kind of devices we are working parallelly. And the advantage is that organic devices, they can be processed using a solution processing technique. So they are cheaper, they are ultra thin, they are flexible, and of course they will be when the final device comes in the market, that will be very cheap. This is our team. You can say from my section, he's our head of the division, Dr. L.M. Pant. Then these are my colleagues. First, I just want to give a glimpse what we have in our laboratories. We have all possible facilities which are required for doing this kind of research, where you have to synthesize organic molecule, characterize organic molecule, fabricate the devices, because these organic molecules are actually very sensitive to the atmosphere. So we have a controlled atmosphere glow box, which you can see, where moisture and oxygen are controlled to 0.1 ppm. Then all possible characterization techniques like surface characterization and structural characterization, these things are available with us. In past some time, which we have done is, the first thing is that we have developed this organic laboratory. We have set up this in last few years, and we started. The idea was actually to start to explore the fabrication of low-cost devices using a bottom-up approach. Bottom-up approach means you start from the smallest possible chain, which is molecules. And from molecule, you go on adding molecules and start increasing the length, rather than coming from the top, which are following, like in silicon, you are trying to reduce the size, and then technology is being developed in order to maintain that. So we start from the bottom, and then we slowly try to add up the molecules till we get the functionality or associate or whatever is required functionality. We demonstrated memory effects and organic layers. We fabricated freestanding conducting polymers. We demonstrated some superhydrophobic organic surface. Some methods were developed, and we did some measurements in some different techniques in organic solar cells and dye-sensitive solar cells. Very little, in very kind of brief, I can give you a glimpse, because the talk is going to be on very basics. So some of the work which is noteworthy or remarkable in our lab, which we done, is like a development of super hydrophobic organic film we have developed. This is the organic film, and you can see the water molecule, which is actually it is totally, the drop is not contacting with the surface, and this we successfully deposited on the substrate also, so that can be utilized. We also, like in dye sensitized solar cells, you see there is a electrode, platinum electrode, which is a very good electrolytic activity for the redox I3. So that is, since it is very expensive, we try to replace it with some organic molecules, and we have made a new polypyrrole freestanding film by which we actually successfully replaced this. And then we also developed a new method for electrochemical designing on TCO substrates. So if you see overall, we are actually we are doing research on organic molecules conducting polymers. They are utilized in organic field effect transistors, memory devices, organic gas sensors, organic dielectric materials, and all such kind of things. As far as the solar cells is concerned, because today's topic is mostly in solar cells. So solar cell activity was started in our laboratories from the scratch. There was nothing actually in 2011. Slowly we started developing in 3-4 years. And so this is our progress. When we started, the world was here, we was very less. Slowly we are also progressing, they are also progressing, but we are progressing with a little faster pace. And probably in next few years, we will be able to catch up them. This is typical characteristics, IV characteristics. And this is the flexible, you can say, solar cells, which has been developed at our lab, which is functional. And it is giving a very good amount of, you can say, power. It can be, we will probably in few, some time we will be able to demonstrate the industrial applications also. This is typical, you can say, fabrication films, different films in this polymer. We are also trying to make, because there are some conducting electrodes are used, which are normally in FTO or ITO. There are different issues with these conducting electrodes. So we are trying to make different TCOs also. Work is going on that also. So like in previous slide, we use P.PSS as a conducting electrode. Here we are trying to develop silver nanowires where these can be utilized as a transparent conducting electrode. And we have achieved a very good seat resistance and up to 60% transmission in these. And hopefully in a few years of time or few months of time, we will be able to develop these. Similarly, the polypyrrole nanotubes also we are trying to develop if we can really utilize them in a whole transporting layer materials in a polymer or perovskite solar cells. And you can see the film or you can say the paste which has been developed after application on a glass tube. It is a fair amount of transparency giving. So you can see that so it is possible. We have utilized, in fact, we have recently utilized this, and it is giving good results. In addition to that, we are also working on organic scintillators materials. These are crystals, and very recently, about 8 months ago, we have been asked to work on the development of organic scintillators, because they are all the organic scintillators are being imported, and we require in kilotons in our place and some other places in India also. So within this period of time, we have developed this much big of plastic scintillator, and you can see it started from here and slowly, and ultimately we need to make about 1 meter long plastic scintillator. This is the work which we are trying to do. This was as far as our work was concerned, but right now the next talk will be as I already said, it will be mostly focused on the very basics. And I prepared this talk keeping in mind only students. So I will be successful if they understand by the end of the talk everything about the polymer solar cells. So let us first see what is sustainability. So if we can say sustainability. So sustainability can be described as the energy that meets the need of the present without compromising the abilities of future generations. Means we should need that energy, but we should not actually deprive them our future generations like like we are doing in the coal or in the doing of the other fossil fuels. We are actually using, we are depleting. See, these like fossil fuels, as previous speaker said, this has been developed over millions of years. Or you can say several million years. And when the discovery was about 200 years ago, and within 200 years, we have depleted almost everything. And so this kind of thing are not actually sustainable, because what will happen after these things go? So one thing is which is actually sustainable, or it is sustainable for at least until sun is there, is the solar energy. So solar energy is, we can say, sustainable energy. So let us first understand what actually solar energy is and how it comes. So let us forget about every other thing, that let us believe sun is a very hot body, and the body is at 5,800 Kelvin. And what is the source of this much, you can say, temperature is these fusion reactions which are taking place at the center of the sun. So leaving these equations, let us consider sun as a black body of 5,800 Kelvin. So it will be emitting a very high amount of energy. So 4 into say 10 to the power 20 joule per second is emitting in all 4 pi directions. Now Earth is at a very far distance, but still, see, it gets about 1,73,000 terawatt of the sunlight, and it is hit at every day. Even a fraction of this power, if you can utilize, if you can convert this power into electrical, that will be, we can say, much more than the whatever energy is required for the whole of the world. Let us consider, if we imagine only this sun, which is actually 5,800 Kelvin, what is it is emitting? So it is, this curve is actually a ideal black body emission at 5,800 Kelvin degree. Kelvin. So now, so this much is coming at the, you can say, outer atmosphere of the Earth. This, if we draw a spectrum at outer sphere of the Earth, when the atmosphere ends, then we will get. But as soon as it start entering in the atmosphere, the gas molecules, water molecules, or whatever other, mostly there's a scattering also. So this is start to reduce. So what we get at the, you can say, Earth is typically this kind of spectrum. So this much is power. So if I measure at the surface, top surface, my energy is 1,353 watt per meter square. Imagine I'm getting, it's a 1 meter square. So imagine I'm getting a power of 1.3 kilowatt in 1 meter. That is a huge power. You can have the same power is equivalent to about 20 normal bulbs. So imagine how much power actually we are getting. And if even after reduction of these things, the power at Earth, what we get is about 853 watt per centimeter square. I have mentioned some things here, 1.5, AM1, AM0, AM2. What are these actually? This is, there's nothing, but see, sun is in the morning, it is somewhere here. In the evening, it goes here. So at different temperature, different times, actually it, you can say the radiation which comes from the sun goes through the atmosphere at a different length. So the ratio of this length divided to the ratio of the minimum, which is supposed to be at the noon, which is here at sun, the minimum distance. So y by x is called as the, you can say, air mass. So it is basically relatively air mass. If sun is, you can say, the radiation is crossing minimum distance, in that case, I can call it 1. If it is crossing 2 times the distance somewhere here, then I can call AM2. And so here what it will be, AM at this point, 0, because it has not actually crossed any of the air mass. So if I say intensity here at this point, it is about 88.8 milliwatt per centimeter square. But you see, as I already said, some part are scattered here and there. So you get some scattered component also. You get something reflected, some scattering, all those things. So overall, you will get about 100 milliwatt per centimeter square. So that is the typical energy which we use in a standard one sun energy. It is called as one sun energy. It is 100 milliwatt per centimeter square or 1 kilowatt per meter square. So imagine it's a very huge amount of energy. So let us come to see what are solar energy. Solar cells. So solar cells are those devices that can convert that amount, that energy which is received from the sun on the earth, 100 kilowatt or you can say 100 milliwatt per centimeter square, to the electrical energy. So as you can see, crux is how much of this energy you can convert to the electrical energy. So that is called as the efficiency of devices. So more the efficient device, even if you have lesser efficient device, then also as I saw, the amount of energy imparted on the earth is so large that it will be, the thing is that it has to be utilized. It can be very useful to the mankind. So now why solar cells should be used? Of course, I believe my previous speaker must have explained those things. So I will go very quickly on these things. It's a renewable, clean, high power to ratio, easy installation, no fuel cost, have long operation life, no product noise. It doesn't produce any, useful in the remote locations, sea, space. Space, it is absolutely, the idea was of the solar cells was only for space. Because when the solar cells was discovered, that time nobody has thought that we can utilize this for the household also, because it was so expensive. So initially research was for space only. We also worked. I'll come to that a little later. But still in space you have very few, you can say, options. But there are some issues also. What are those issues? These cannot be obtained in night time. They are expensive, stored in batteries, and so these are different issues. Cleaning issue is also important one. So now let us see the evolution of solar cell technology. Actually, it was developed they discovered somewhere in 50s. Initially, as I said, not much work was done towards the industrialization. So there we can divide it into three different generations. First generation were mainly vapor-based technologies. Second generations are when you started to industrialize, when the efficiency was not at all that much important, but you wanted to have some modular kind of sources, thin film. And now third generation, which is present generation, which is usually for the organic waste. So in first generation were monocrystalline silicon and gallium arsenide, mainly these solar cells, and polycrystalline solar cells were also developed little later. And in second generation, amorphous silicon solar cells, which is also a thin film. These are second generation technologies, are thin film technologies. These are thin film. These are, you can say, little bit bulk. Though polycrystalline is, you can also call them a little thicker, but these are very thin film. Their active layer is very thin. And then third are organic solar cells, DSSCs, perovskites, and quantum dot solar cells. So let us see. First, before go to this, let us see how a Pn junction solar cell works. Actually, all the solar cells, or the, you can say, basics of them lies under the Pn junction principle. So as I could have a glimpse of, because these things were not working from previous speaker, he must have also explained, but let me also just say. So these are like you have p-type and n-type semiconductors. When you actually mix them, or you can just fuse them together, what happens? Their Fermi levels are different. So the first condition is that Fermi level has to be aligned, because Fermi level for one system has to be constant. So now, right, when we actually fuse them, so these are actually instantaneously, okay, say for a very small time they are different, but they have to align. This is the first condition. Now, if they have aligned, there you see there is an abrupt gap here that cannot be abrupt. So what will happen? See, electrons from this part will try to move here, and the holes will try to from this part to move here. So what will happen? Electrons will move from one side to another side, from like n side. Electrons will move from the n side to p side, and holes will move from p type to n side. And then what will happen? This will actually generate a potential, and that potential will try to oppose the movement further. So after some time, So these are two processes. One is drift, and another is diffusion. Diffusion is because of the concentration gradient of electrons. They are moving from one side to another side, and drift is because then you have a potential difference developed, and that potential difference is actually opposing those two. So after some time, there will be actually a thermal equilibrium. In thermal equilibrium, what will happen? The situation will be like this. A Fermi level is aligned. And if you see, there is a potential difference developed that is called as a built-in potential. If I see between this point, this end and this end. So this potential difference is actually very important. And this potential difference is, you can say it pulls the electrons which are generated, which are here, or holes are here. So this VBE is very important, I must say, and this actually is, you can say, it is not, you can say, it is not actually open circuit voltage, but it gives you the open circuit values. How much is the open circuit voltage, or you can say limit of the open circuit voltage for any solar cell device. So now, if I say this, okay, this is typically a solar cell structure. If I connect with these, you can say connection. Make a connection with a metallic wire, then it becomes my solar cells. Now there is another issue. If I directly connect this, you can say semiconductor with this metal, a semiconductor with this metal, with this will work? No, it will not work. Why it will not work? Because now it is a metal, it is a semiconductor. So now I am having a metal semiconductor junction, and there will be actually a, you can say, work function difference between these two. So it will be creating. Or you can say at the end project, it will be having two back-to-back diodes here and here. So effectively, there will not be any current. So you do whatever you want. But so for this purpose, what we do technologically, so you make ohmic contacts actually. So there is a different process of making ohmic contacts. So let us believe these are ohmic contacts. And so suppose if we see a photon falls, and for what photon will do, an electron hole pair will be generated. And these electrons will be collected because of this potential, and these holes will also, you can say holes will also move, or you can say electron can come from here to here, and the electrons flow in this circuit and current flow. So this is the principle of the solar cells, how a solar cell works. So now we have understood what a solar cell is, how a solar cell works. So some of the important parameters which actually define the performance of a solar cell. Let us see what are those parameters. If you go, or if you see anywhere solar cells, there will be definitely you will be seeing certain parameters associated with those solar cells. So for students, let us see what these parameters are. So okay, this is my solar cell, and it is illuminated. So there will be some, you can say, if I connect through this circuit, so some current will be flowing, some voltage will be generated across these two terminals, and some current will be flowing. So that voltage V and that current I, if you multiply them, you will be getting the effective power. So suppose I remove this resistance. If I remove the resistance, what will happen? This will be actually an open circuit. No current will be flowing. So that is the maximum possible voltage which can be generated by a solar cell is called as open circuit voltage. If I remove this, so that is the, but this is the voltage only. It is voltage only. There is no current. So imagine if I am drawing the maximum, if I'm, you can say, seeing maximum voltage, but no current, actually it is of no use because power is zero. Power is V into I. So this is called as the open circuit voltage. Keep in mind, I will be using open circuit voltage at several places in my next slides. So what is open circuit voltage? Next thing is that, okay, I remove this resistance and short it from this point to this point. So what will happen? There will be the maximum possible current will be drawn through this circuit. But at the time, what will be the voltage? Because you have short those points, the voltage will be actually zero. So you have now zero voltage, what the maximum current. So that is the, by doing this way, you can derive what is the maximum possible current which you can draw from a solar cell. So now I have understood two things. One is the maximum voltage which I can generate, that is open circuit voltage, called as open circuit voltage. That is the next is the short circuit current, which is the maximum current which I can draw, but that is at the actually zero, you can say, voltage, that is short circuit conditions. So these, I got these 2 points. It's a VOC where the current is zero and ISC where the voltage is zero. So, but these 2 points are actually useless. as far as the power drawing is concerned, because there is no power. So if I try to draw a power by changing the, you can say, load value, this is the impedance of the external circuit. If I change the impedance of external circuit, in that case, I will be following a path which is like this. So I have actually taken 3 points, P1, P2, and P3. So at this point, whatever power I will be drawing is this amount of power. Here I will be drawing this amount of power. So in this, if you go on following this path, you will get a point that is called as a P maximum, where you can draw the maximum power from a solar cell. So ideally, we should be aiming, all of us should be aiming to work on this point, but it is not actually in our hand. But for the so this is the maximum power point you can imagine. So for this power, so maximum power point means the maximum power now which you can draw from this particular solar cell at this much illumination. So at this point, now if I say this power, if I can say this power, how much is this power? I can very easily calculate, multiplied by Vm into Im. And if I consider ideal theoretically power, see what we wanted. Ideally, we wanted that, okay, actually this is my solar cell, this is giving this much short circuit current, this much open circuit voltage, but I want this much short circuit current at this VOC, at maximum OAC, maximum ISC. That is not possible, but this is what we wish. So if you say what we wish and what we get maximum, if you define this ratio is called as the fill factor. So what is fill factor is, okay, we wanted this much, but we have got this much. So suppose I get 50%, so my fill factor will be 0.5 or 50% of that. If I have to define the efficiency of a solar cell, in that case, I can very easily say for this particular, I will consider for the maximum power. So maximum power divided by the whatever is irradiated. Suppose at one sun, I am irradiating with 100 milliwatt per centimeter square. Then here it will be 100 milliwatt per centimeter square, and then power maximum which I can draw. So this comes out to be open circuit voltage multiplied short circuit current multiplied by fill factor divided by the radiated power. Fine. So now, as we saw from the you can say animation of the PN junction, what are actually the basic steps, or all steps I can say there. So first was actually photon was actually absorbed. The first condition is that the light which is falling on the solar cell, it should be absorbed. Now, if it is absorbed, then what will happen? See, it can be absorbed. It can generate electron hole pair, but they immediately recombine. Then what will happen? So first thing is that they should actually generate electron and hole pairs in inorganic semiconductors. But if you go to organic, if time permits, I will come to that also. They are actually not electrons and hole pairs, but they are excitons. So if electron and hole pairs are generated, then they should not recombine actually. Before they recombine, they should be separated. So we should have a mechanism which separate positive and negative charge carriers very effectively. And then these charges should be, not only they should be separated, but they should be collected at the electrodes also. See, like in this animation, I explained that importance of the ohmic contact. If there's no ohmic contact, those charges may be separated because of built-in potential, effective built-in potential, but they will not actually move into the external circuit. So these two has to be collected at the external electrode, and finally they have to move into those. So all these processes, you can say all these four process has to be you can say efficiently, or we have to design our solar cell materials or select solar materials in such a way that these conditions are met. Now let us come to the first thing, which is the absorption. Absorption of all the you can say radiation it depends on the band gap of the material. If a radiation falls in this you can say material, it's a material with valence band and conduction band with some Fermi level. So if the you can say radiation energy is less than this gap, it will be going you can say unabsorbed. It will simply transmit. And then if I have a you can say material okay, photon radiation is also much beyond this, then it will also pass through. And if it is in between these two, then it will be absorbed. But the ideal condition is that this from the bottom of, or you can say the top of the this band to the bottom of this band is the ideal energy. So one is the band gap. So what can I do actually? In order to effectively absorb the radiation, I have to actually reduce the band gap. This is what I understand from this particular thing. But if I go on reducing the band gap, will it work actually? As if you again go back to the animation part, see there was a built-in potential which was developed because of the difference between this gap. So this gap, if you go on reducing, the potential will actually try to go on reducing. So there's a trade-off between these two things. How much you can say band gap of the material is good and how much current you want. There's another thing. It's a band gap only. It's not only band gap of the materials, but there's a thickness also. See, even if it is having a very you can say a low band gap, but thickness is very low. So then also the you can say the radiation will not be absorbed. This is particularly applicable in case of thin film technologies, not in silicon standard monocrystalline solar cells, because there is a sufficiently thick substrate is there. But when you are in organic solar cells or some other, there is thickness plays a thickness is a few, you can say nanometers. In that case, the thickness also plays an important role. So how much is thick, more the thickness, the things will be good. So if I just go through the you can say band gap of different materials. See, this is what from the last slide we understood, that band gap is very important for absorption. So and below the band gap, okay, if energy is less than the band gap, then it will not be absorbed. But if energy is more than band gap, we believe entire spectrum, entire energy will be absorbed actually. So this is for different materials. Like if I say standard crystalline silicon, the band gap is about 1.1 electron volt. So what that means actually, this entire energy, or say the entire spectrum, this entire spectrum will be absorbed in the silicon solar cell, and all these things will be actually simply passed. You can say from there, or you can say transmitted from that solar cell. So only this much is the maximum energy which can be utilized. If you can say, if you just can look into this spectrum, the silicon falls somewhere here, so it is about 44.7. So it is about 60%, 60% of the you can say. So maximum efficiency can be only 60% because other has been passed. So we can actually, suppose if you use indium nitride or gallium antimonide materials, so then we can have a you can say absorb about 90% of the energy of the solar spectrum. But it is very difficult to extract that energy, because in that case you will not be having a sufficient built-in potential to actually effectively separate all electron and hole pairs. So let us see, there's one more important thing. What is the, this is optical loss. See, whenever a radiation fall on any surface, some part of it is invariably reflected. It depends how much part is reflected. It is actually, you can say, described by this formula. This we all know, we must have understood. If the refractive index of this is say 1 air, and then if it is, suppose it is glass, I can imagine 1.5. So if I say 1.5 minus 1, forget for the time being k, 1.5 minus 1 divided 1.5 plus 1, so 0.5 to 2.5. So about 0.8% from this surface, 0.4%. 4% from this surface, or 4.5 from this surface. So 8% is anyway invariably is going to be lost. So you cannot have absorption in ideal condition. Even you have the best possible you can say material which is absorbing 100%, it cannot absorb more than you can say 92%, provided the refractive index is 1.5. So now if we see all these loss mechanisms, if I sum it up, so it is like that. If incident light falls on a surface, if it is coupled to sunlight, it's valent group, some part is reflected away, it is lost. Also, the coupled part is also, it can have, means there are two things, though it is coupled, but it will not be absorbed, it will be transmitted. That is also a loss. Then the things which are actually, you can say, absorbed in incident photon, there is also two possibilities. It can create electron charge pairs, or it cannot create. So if it creates, that is very good. Then if these charges, although they are created, but they recombine, it is a loss. So then these, suppose let us consider these are not lost. okay, then if they are separated, it's a very good thing. So then finally the charges are collected if they are not recombined. So these are all like in between we see the loss mechanism which are important. So contact materials are important. Metal semiconductor thing we have to also take care very well. There are some kind of recombination, radiative tape assisted surface in between also, the way I said the charge recombines. And rise temperature is also an issue. I will come to when I explain shortly what are the different other methods for each. So let us say the same thing in continuation of the same thing. What is the maximum possible limit of an efficiency by which means I can get maximum possible efficiency for any particular solar cell? So there are certain conditions. So like as I said earlier, there is valence band, there is a conduction band. If the you can say photon energy is less than the band gap, it will not be absorbed at all. If it is more, so if it is exactly this much, it will be absorbed, fine electron hole pair will be generated. But if it is more, then what will happen? So this electron, see, this the hole is here, electron is here. So electron will immediately come to the this level, the bottom of this, by you can say emitting the heat. So this excess amount of energy which was actually absorbed, it goes into the heat of you can say solar cell. So that's why the solar cell actually get heated over. So the temperature of solar cells is also it increases. That is also you can say loss. So spectrum loss, number one, spectrum loss, it is of course, as I said, there for the silicon, suppose I believe only this much amount of spectrum is will be utilized. This much is anyway going to be totally wasted. So spectrum loss, so whatever is not absorbed is total waste as far as the solar cell is concerned. Let us consider this. Next, if absorbed photon is having higher energy, this much energy, then of course it will be emitted in form of heat. The temperature of the solar cell will also rise. Though temperature will rise, so it will also emit, you can say, it itself will start emitting the black body radiation as the temperature is higher. And then next is the impedance matching. If you don't match the impedance, the impedance is, you can say, not exactly you can say matching with the impedance of the solar cell. In that case, there will not be actually optimum flow of electric current. So that is also a problem. And then recombination losses, of course, this whatever see if it comes from here, see you have actually you are just imagining one thing according to your favor. Okay, I have irradiated with this much of photon and it has been absorbed, electron hole pair are generated, but who stops it from recombining back? It's equally probable. If absorption is allowed, emission is also allowed. So that is also a loss. But before they actually, as I said earlier, before they recombine, you have to actually collect them. And there's, as I said, the temperature of this cell is also rising. So a black body radiation is also important. So if we just go through this, so for any like solar cell, this is the only usable electrical power. If I plot on the band gap, so if you say around 1.1 electron volt or 1.4 electron volt is the maximum power for I can draw. So I should design my materials in such a way that I can get this much power. So this band gap is usually for gallium arsenide, which is a direct band gap material. Silicon is also not very far, though it is indirect. Indirect and direct difference is actually because either the phonon interaction is necessary in order to absorb the photon. So this was this is a famous paper of Shockley and Quashier in 1961. It is still valid. So this defines your maximum possible efficiency from a solar cell, a single junction solar cell. You can have multiple junction solar cells also. If time permits, I'll come to that also. So, so for single solar cells, like a single junction silicon solar cells, you cannot have more than 33% efficient solar cells, even if you try your level best. So now let us come to what are the important properties for material selection part. So first is we understood that there should be an optical energy band gap. absorption coefficient should be very high. If absorption coefficient is high, in that case, you can have a later, you can say, you can have a thinner surface in which you can absorb more amount of radiation. There should be a good carrier mobility. Carrier mobility means the rate by which electron and hole move inside the material. Then large carrier lifetime. Carrier lifetime is the, you can say, once electron hole pair is generated, the lifetime of that electron hole pair before they recombine is the carrier lifetime. So it should be as large as possible. Large built-in potential so that you can effectively separate the charge, and diffusion length is something before. Diffusion length is actually a length over which they are effectively, we can say, recombining. So, and surface recombination should be small. Fine, this is okay. And what are the other things which we can do? We can also make, to avoid the reflection losses, we can coat some anti-reflection surfaces over the top surfaces. And we can also texture the surface. The texture surface means, so if you have, you keep on like making some kind of holes kind of thing in a surface. So by doing this texturing, actually you are increasing the surface area. So if a radius, it is actually, if radiation falls on that kind of texture, it's very difficult to go it back. So you are actually trapping that radiation. And then you have a multi-layer coatings also, that is by that way also you can increase. Then metallics, better metallic contacts and high conductive contacts are required for, they have less series resistance. Then N-type, P-type, these are the improved PCOs for like, though these are applicable only for the, mostly for the organic parts. So based on the type of single crystals used, silicon solar cells can be classified in 3 different categories: single crystalline, polycrystalline, amorphous silicon. Single crystalline solar cells are those where actually used from the pure silicon single crystal. Since the monocrystalline silicon is pure and it's a very, you can say, defect-free, they are very expensive, but the efficiency of the cell will be very high. We have seen some reports, even 27% efficient silicon solar cells from the monocrystalline. So let us see a typical fabrication process by which we do. So how we get a silicon, you can say, well, commercially, if you want to buy, we don't want to go into the crystal growth and other things. We just want to start from the wafer. So you get a silicon in form of a wafer. So this is a wafer. So there are certain, you can say, damaged surfaces at the top. So you just cut those things. So you saw those surfaces, and effectively you have got this a flat top and bottom kind of surface. And then you texture its surface. Texturing can be done by many methods. So usually people do by etching. So you etch it. So you have several pits created on this top and bottom of the surface. And then because it's a P-type surface, so now you have to make a junction. So in order to make a junction, you dope the entire surface, because you cannot dope it selectively. You can dope selectively also, but usually the bigger industrial process, the entire thing is put under a, you can say, phosphorus environment, like in POCl3, all those kind of thing. So then once you dope this, so you get a N type of surface over this you can say textured surface. So now effectively you have got a PN junction. So, but if you use the same, try to use the same thing, actually, and it will be totally shorted from this to this. So you have to cut this part also. So for this, you actually, as you cut these edges, and then you coat anti-reflection coating on the top surface of that, and then prepare some front contacts and then back contacts also. You can remove this surface also by etching, this part also by etching, and then by co-firing, actually you make a good, you can say that's your solar cell is fabricated. Fine. And if you measure by, you can say, normally you should not apply voltage and measure current in a solar cell, because solar cell is a current generating device. So if you apply voltage, that is making, you are killing, actually, you are comparing two voltages, and then you are trying to draw on an external circuit. So this is, ideally you should draw the current from the solar cell and measure that current at the different potentials, whatever potentials also. Now, as I said in earlier, so that BARC has a history, like we were assigned when our solar program was probably, when our space program was initiated, nobody was giving solar cells, because in space, you need to run a power systems inside a satellite, and there are only you can say solar cells which are actually the source of power. So somewhere in 70s when that was started, so it was thought that okay, people are not giving us solar cells, so so VRC was assigned to make space quality solar cells at that time. And say from 70s to 80s, within say I think about 10 years period, we were able to produce successfully a good amount of you can say working solar cells. Those have actually been you can say incorporated in the satellites. So this is a typical fabrication step process which I have taken from the technology transfer document of our this development. These are just these processes which I have explained. The efficiency of those solar cells was 14.5, and at that period of time, the efficiency internationally available were also around 16 to 17%. They were very good surface. This is the recipe which which BRC has developed and transferred the technology to outside world. These are those solar cells which were actually made in 80s at BARC. They are working. They are still with me. And these solar cells were actually placed in these two satellites, Bhaskar 1 and Rohini 1. And the technology of this fabrication, these are actually fabricated at BARC only, these solar cells. They are that much old. You can see by these contacts that these are old, but they are still working. If I see to test the robustness, the same solar cell, this is the solar cells on which I did the measurement. These values, which was in 1984, I have taken from the technology transfer document. These were around on an average values of the solar cells was open circuit voltage about 0.6 volts, short circuit current about 38 milliampere per centimeter square, fill factor around this, and efficiency was that time of this particular thing is around 13.7. This batch 13.7 efficiency, and if I measure the same thing now, then it comes about 0.57, 36.2. So over the period of like 37 years, if you see, they are such a highly reliable, you can say, solar cells which were developed by us. And I don't know if the satellites though are decommissioned, but I believe the solar cells supplied by BRC are still working there. We have tested this. How much time I have? Okay, so these we you can say we tested. These measurements are of last year measurements. Radiation hardness, input impedances, temperature variation, everything is done. Because of that, you can say in the space, you need to see the solar cells. It should work at a very high, you can say, temperature difference ranges. Like in the when your satellite is not facing the sun, that time temperature can be very low in several, you can say, up to minus 200, 300 degrees centigrade, minus 200, 250 degrees centigrade. And if it is on the positive side, it can have a very high temperature. So solar cells, when it is used in a space application, it should be you can say it should be operable in that high temperature ranges also. Now the polycrystalline is also it's the same thing. Like only thing is that you use polycrystalline mass. What you do in this case, actually you don't use single crystals, but what you do, you melt the silicon, and after melting the silicon, you pour it. Once you melt the entire silicon, and then you pour, or you pour in, you can say, make a brick kind of thing, then cut those bricks into small wafers, and then make the solar cells. So this is these are slightly lower efficient solar cells, but still they are compared to, because you need to spend a lot of money to get a single crystals. So this is a cheap process, less energy is required, and efficiency is also not very low. So if you say 25 to 26% for molecrystalline solar cells, for polycrystalline, if you can have 20 to 23%, it's a better trade-off, because if you are spending, it's easy to fabricate. And so this is just for the polycrystalline. Now third was the thin film technology. Why you need thin film is to reduce, of course, reduce material quantity, fabrication cost is easy, and you can tune the material properties in thin film. That is important thing. And one important, I will just see amorphous silicon solar cells, where the thin film of amorphous is actually deposited. And then this film, when it is actually, there are a lot of dangling bonds here. These dangling bonds you need to take care because otherwise there will be a lot of you can say surface recombination here, or you can say recombination here at the dangling wall side also. You have to terminate with the hydrogen. So by terminating this silicon, amorphous silicon by hydrogen, you actually increase the bond length also. You can say band also for more than that. And then, but there is one difference also there. So it is silicon, it is pure silicon. So you need to have P-type and N-type layers, and you have to sandwich this layer in between those two layers. So absorption will be actually taking, photon absorption will be taking actually in the amorphous silicon site, and it will be actually collected by P and N kind of thing. This is the advantage, disadvantage of all this amorphous silicon solar cells. So this is a typical structure where you actually make an amorphous solar cell, where you have glass, then TCO, then P layer and N layer, in which you have an I layer, which is actually absorptive layer for this. And so you have P type and N type, and you can say built-in potential between P and N type is work as a driving force for you can say collecting these electron and hole pair from air. So if we now we see if we compare these things, then the amorphous silicon is of course about 7 to 13% efficient, very less, but you get advantage of you are spending less you can say silicon, and it is easy to form. So there are some other like CIGS. They are same kind. It's just to like completion. I have put 1 or 2 slides. So these these are same things actually. PIN structure. So you have you have actually sandwich between P and I structures. Sorry, P and N structures, a simple I structure. Similarly, you have CDS, CD solar cell, quite reasonable efficient, about 21%, where you have cadmium sulfide, N type of cadmium sulfide, P type of germanium, and then you have in between you have a small layer of the cadmium telluride, which actually absorb the radiation and generate electron hole pair, which are collected by these two. So there's another thing is that you can also use 3rd, 5th semiconductors for making these solar cells. And now there's one important thing I want to emphasize here. So there was an issue actually of the band gap. So the material which okay, so there's a large band gap. So what happens to the radiation which actually is having less energy than this much band gap, which is so there is a tandem design. In what you do at the top surface, you have a material which is having higher band gap. So what it will do, it will absorb the higher energy, but it will pass the lower energy. The lower energy will go to the next step, where you have actually added another solar cell, another junction actually, which is having lower band gap, so that some of the energy will be absorbed from in this, and then you go to the 3rd you can say layer, where you are having at the bottom cell, which the energy is, you can say band gap is very, very low, say about 0.65 if I consider germanium. Similarly, like indium and antimonide also, it's of similar electron volt. So this is a structure which is actually has been experimentally proved, and this much spectrum is absorbed in the top surface. Then this green part is in the middle junction, and this part in the bottom junction. So now you can increase the so you can say using concentrator also you can increase the intensity, solar intensity also. So this kind of solar cells with a multiple junction have actually proved to be actually it is more than 43, now it is 44 point something. So at 400 sun, this is a typical design for the solar cell. So this was okay. This up to this we were actually going on you can say inorganic solar cells. So can I ask how much time do I have or I finished my time? Professor Rao.
Sir, it can continue up to 5 minutes like this, 5 to 10
Okay,
minutes.
fine. So I will try to go very quickly, because then I will explain about one or two, just like to have like
Okay,
what is the organic solar cells.
Okay, sir. Okay.
So this was like inorganic solar cells. So when everything was going good, everything was fine, we were doing good, good efficiency, solar cells are available, thin film solar cells are also available, everything is good, then what is the problem? Why we should go for the organic or something like that? So actually, there are some issues with the inorganic materials. What are those issues? They are expensive. You need very high purity materials like silicon. You need up to a very high purity. Even in case of amorphous, you need to have a very high quality silicon material, starting material. Fabrication process is very complex. They are not flexible. And some solar cells use toxic materials, like in the last slide I saw about cadmium. There's some sulfur and cadmium materials are there. They are very toxic. So what we should do actually, there can be a solution in form of organic materials. What are those means? What is the advantage? First, let us see. Low cost. They absorb good amount of light. Processing is easy. We can do in laboratory also. For like making these solar cells, you need to have a very high quality industrial process and expensive instrumentation, expensive equipment, and can cover large surface area cost effectively. They have tunable property. The most you can say the best I would say, or say the advantage with the semiconductors are you can very easily tune their properties. They are eco-friendly, biodegradable if you choose materials, but there are some issues also. Number one is the evolving technology. Technology has not yet matured, so there are still issues. There are many areas, gray areas, we are not yet resolved. Efficiencies are relatively poor, though perovskites have achieved reasonable, quite reasonable efficiency, but still they are lower. There are some other issues, degradation issues, and those things. Batch to batch variation. These are not actually made on these organic materials or polymers which we use in laboratory. We purchase from outside, and they are not actually made on a mass scale. So from different batch to batch, you have variation in the properties. Then purification is very difficult in case of inorganic materials. So let us understand the basic difference between inorganic and organic semiconductor. So number one, organic semiconductors are basically carbon-based materials which possess semiconductor characteristics. Now, if you see inorganic semiconductor, see there is a these are crystals. This is a solid state device, and it has a very, you can say, long range order. Long range order means if you have a long range order, you all are physicists, you know there will be a long range order. If it is a long range order, it's a periodicity is maintained. It is a single crystalline form. In that case, there will be a band. There will be bands. So, and the band will be, if it is an entire single crystal, the band will be actually extending from one end to another end. So you will have bands, you will have valence band, you will have conduction band. Once an electron and hole pair is generated, the you can say the or electron is you can say in this, and it is detached to this hole, and then it is ballistic. So then it is like, it behaves like an absolutely free electron. It can move with any speed. It can take any energy, even a small amount of energy it can exit. But this is not the case of organic semiconductor. So organic semiconductors are actually small bunches. Actually, they are placed at very near, you can say, distances. There is no long range order. If no long range order, in that case, you will not get this kind of band structure, but you will get you can say small localized band. But though the levels will be matching, but they will be, you can say, separated with the small gap. So suppose you have some electron here in this case, and you have another level here. So it has to actually hop from this point to this point. There is no continuity. So this electron doesn't feel to be, you can say, being in the level which is actually adjacent to it. So there is a very big probability so that it can recombine. So now you have actually excitons, not an electron hole pair. So there is a very good probability that these excitons can be actually recombined. So major difference if we see between these two is an exciton form. So if I say if in the analogy of our structure in the case of silicon solar cell, if we try to make a similar structure using my polymers, if I take N-type polymer, which is called usually acceptor here, P-type polymer called as donor here, there's a slight difference in nomenclature. If I add those two and then two electrodes, cathode and anode, and then try to do this, in that case, this is this ideally it should be like this only, but it will have certain problem. Why it will be having a problem? Let us understand by the similar Venn diagram which I actually tried to explain earlier. Now actually it is not a case as it was in the case of silicon solar cell. So now you have an anode, you have a cathode. So if I actually combine and all of them and make it together in a one system, it try to make, and then I am making a small, you can say, structure where it's an anode, cathode, one donor, one acceptor are joined together, and this, you can say, entity has been formed. So let us consider in the case of that, the Fermi levels are aligned in the thermal equilibrium. Though, please keep in mind when we illuminate the Fermi level concept goes, it doesn't believe in the same way. It doesn't work in the same way like in normal conditions, but for the, you can say, understanding, we believe that this is constant. Now, if a photon is falling, in that case, now what will happen? This electron hole pair is generated, but now these are actually, sorry, it is now not an actually electron hole pair, but it is an exciton. They are not separated. If they are not separated, they are an entity which is having a zero effective charge. So if it is having a zero effective charge, because positive and negative charge are, you can say, is neutralizing each other. The entity which is there, the exciton, which is having a zero charge. Now, though there is an, you can say, potential difference between these two, or you can say there is an, you can say, slope for this if electron to move here, but the electron will not move to this side only, because it is actually, it is associated with the hole also here. So now there is another problem of the low efficiency is because this exciton can move in any direction, in any 4 pi direction. So let us, for our convenience, we believe that it actually move in this direction only. That is the, we can say it is, it can move in all 4 pi direction, but we have conveniently assumed that it believes here. Now, if it comes at the junction, you see there is a gap here. So this gap and this gap, that provides a, you can say, motivation for these electron hole pair to get separated. Now this energy, the more this energy, actually it's a more the excitation diffusion, excitation separation. So now it was exciton diffusion. Exciton diffusion is also less probable to reach up to a boundary, and then there is an exciton dissociation. So this much amount of energy, it's a activating energy, is required to have dissociated. Now, once they are dissociated, of course, they can see this potential difference and they can move towards their respective electrodes and collected, and then finally collected on the electrode. So now you see there are a lot of problems in all this. The first thing is that exciton which has been created, it's a very much probable that it will move, it will actually recombine. If it doesn't recombine, it will move, it will reach at the interface. There is also a very less probability. Even after that, they can actually recombine the, you can say, mobility of these materials, which are organic materials, is not that much high like a silicon. So they can come from coming to here is also not, you can say, so very efficient process. They can in between also, you can say, get entrapped in somewhere or get it recombined with this also. So that is why these, you can say, polymer solar cells are very, very, you can say, low efficiency solar cell. So let us see, this was actually a, you can say, active part of the solar cell. We can call only that part where the exciton, if it moves from this point to, see, we have electrodes here and here. So only this much part is actually available where the electron can be collected. So this is called as the diffusion length. This much is the diffusion length. And that is the reason why the typical efficiency of bilayer solar cell is very, very poor. Actually, 1% when I write is actually very, you can say, I have multiplied with some number. So, but it is actually in a fraction of a percentage. Because you can see excitant cannot actually cross this area. And you cannot have this much amount of thickness active layer only. So what is the, you can say, what we should do actually? That means that the structure which we're working in silicon will not going to work in polymer solar cells. So there is another thing is that if we cannot take excitant to the boundary, but we can bring boundaries to the excitant. Wow, how we can bring the boundaries to excitant? Actually, we make a blend. And that is called as the bulk heterojunction. When you actually make a blend of donor and acceptor materials and then prepare and then deposit between two electrodes. Now what happens if an electron and hole pair is generated, it invariably will see very close to it, there is a boundary. So boundary is necessary in order to, you can say, dissociate an excitant. So now electron hole pairs are supposed generated, but still you need, there is another technological challenge. Even if they are separated, hole and electrons are separated, but the electron has to go to this electrode, hole has to go to this electrode. So there has to be a continuity on the same material without even changing the material. So that is also a very big challenge in this. So these are actually, you can say, main reasons why we expect a very low efficiency in polymer solar cells. But now there are certain, you can say, so there is one method by which we can actually do this, a nano structuring. This kind of image, if you make, see, you have a contact, this contact, and one, you can say, and active layer has been deposited in this way. Actually, this is the ideal structure, and I have made like this one. So electron hole pairs are generated here, and then one is collected immediately here, another is here, and then it can go to the contact. So this is one way, but this is ideal way. Still, not very, you can say, good. But this actually, by doing this, you can actually increase efficiency with a sufficiently amount. Now, right now, about 10 to 12% efficient polymer solar cells, bulk heterogeneous solar cells are available. So these are the loss mechanisms. I think I should maybe I think I can stop here because it will take otherwise much long time. So, you know, if I explained till now, I have explained the working of photovoltaic solar cells in case of inorganic solar cells, organic solar cells. I discussed about the polymer solar cells and just some of the, you can say, issues with the bulk heterojunction solar cells and issues with the inorganic solar cells. So what do you, can I, Professor Rao?
Sir?
Yes.
Sir, would you like to continue for like our talk is about to come?
No. I can continue, but because I have taken a little longer time, so I can. I will directly go to maybe I will directly go to some of the work, some of the like methods how to improve the efficiency within actually maybe 5 minutes. I will complete that part also.
Okay.
I will very quickly go to that.
Okay.
So let us. Okay. So I leave this. All these things are very.
Okay, sir.
I will go towards end. This is actually I will just explain the process of fabrication process. This will be useful for the students. So how we fabricate the bulk heterojunction solar cells. So you have you have a ITO coated glass which is commercially available in the market. So what is that it's a glass actually. 1 minute, pointer option. So it is a glass, and ITO is coated over there. Indium tin oxide is a conductive surface, which actually is a conductor, but it at the same time it transmits the light. So you can.
Anil sir.
Yes, sir.
Could you please concise your topic to 5 minutes below?
Yeah, 5 minutes. So then then you make by chemical etching, you can develop the electrodes. Then whole transport layer is deposited by P dot PSS. Then active layer is deposited, and then you deposit the electron transport layer, and afterward you deposit the back electrodes, make the contacts, and then as soon as this light is absorbed, exciton is separated, these flow into the external circuit, and the current is flowing. So with this, this is like some of the our laboratory experiments. This is the devices which we have actually fabricated. This is a working 2-inch by 2-inch polymer solar cell. This is working flexible solar cells, which I showed earlier. So let us come to the how we can actually improve the efficiencies for the, like, if you want to make them sustainable, you need to improve the efficiency, you need to improve the you can say efficiency, and you need to improve the you can say stability also. So as I earlier explained, see, this is the band diagram, and this is the structure, the acceptor and donor difference. It actually tells you how much the open circuit voltage we can generate. And then this level difference between these two, actually it defines the current level in the, or you can say short circuit current of this device. And there is another thing which is the mobility. So what are all possible ways to improve the sustainability of these devices is that you increase the open circuit voltage by actually, if you can alter these levels, acceptor and donor levels, and you can increase, if you can decrease the gap between these two levels to increase the short circuit current, and the charge collection by work function, increasing work function, selecting best anode and cathode materials. So we did the altering of HOMO and LUMO levels by you can making the graphene composites, and conduction through active layers was improved by again making graphene composites of some of the acceptor molecules and some donors, and the absorption is also improved in the active layer by increasing the. So when we actually make graphene composite of P3HT and one acceptor PCBM, we found that the energy level of these two were changed. So these were actually original energy levels for P3HT. These are original energy level for PCBM. The levels of PCBM were favorably changed towards the this side. So actually, effectively, you can say the open circuit voltage which is actually difference between this level and this level was increased. The same thing was observed by us experimentally also, and this way we increase the efficiency. Another thing is that you can say improving the charge transport by making graphene composites. So if we see, this is actually a, you can say visual presentation of how actually carriers are moving after application of potential. So this is for the pure, and if we try to, when we deal with the graphene, in that case you can see the movement, or you can say mobility of the charge carriers has been increased. So by doing this, the efficiency has been increased. So this is done. Another thing which we did was actually one by one, layers by layers were actually deposited over one layer over the other layer were deposited, and there were several 5-6 layers were deposited to increase the absorption. But this actually created another problem of the charge trapping, because you have different layers that are imperfectly added to you can say each other. So there is a source of charge trapping here in between. This is actually understood by the impedance spectroscopy. So what we do by solvent annealing, if you actually anneal it and expose it with the solvent, you actually are able to perfect the surface. And you can see it has been reduced from like 2 circles to 1 circle. So all these things, by doing this, we effectively increase the efficiency of solar cells, and by increasing the absorption, by increasing the you can say changing the energy levels, by increasing the you can say by making graphene composites. And the third thing was to improve the mobility by these graphene composites. So in order to summarize, we improved the efficiency was demonstrated by altering molecular levels using graphene PCBM composites, P3P in P3P HT-PCBM solar cells, and enhancement of charge carrier mobilities of conductors polymer using their graphene composites, and improvement in the absorption by deposition of higher thickness active layers in DTBT PCBM solar cells, and then by actually solvent annealing by homogenizing these you can say layers. Now to acknowledge some of the figures, actually I have taken from the internet, some of the figures, not all. The animations are mostly made by me. This representation is purely for academic purpose actually. And with this, I thank you and thank you very much. I'm open if you need, if you have any questions, and I will be ready to answer. And I'm sorry I have taken a little bit more time, but fine. Thank you.
Thank you, sir. Thank you very much for your informative and research.
Before the questions,
So if anyone have questions, you can ask to Dr. Anil Kumar Chauhan, sir. So sir is on the, so sir is waiting for your queries. So if you have any queries, just you can unmute your mic and then you can ask the questions.
See, this lecture is actually only for students, I would say. So I will expect at least I have put so much efforts, and so if they have understood, actually, I will request them to at least raise their queries and doubts. Yeah.
So, Dr. Jovan Nataraju here, you please adjust your camera in such a way that you are fully visible.
Now I'm visible?
Yes, yes,
yes,
yes,
sir. Okay.
Yes, sir.
Okay.
So otherwise, the participants, you can also just leave your message on the chat box so that we came to know that your queries, sir.
I have a question.
Yes, sir.
First of all, today's lectures are also very good, and a person like me who is not from this field of science, I could understand the fundamentals as well as how the devices are made, how the materials are selected, how the materials are tuned for a given application, and also how the device is made. And while discussing about the device efficiency and other things, the theoretical factors as well as some practical aspects are also shown on the efficiency part. But when the device is converted into the real panel and when we draw the power, it also is subjected to a lot of environmental effects.
Correct.
So how much efficiency loss you expect over a period of time, say given 1 year, 2 year, 3 year, 5 year, or during the lifetime?
As far as the silicon solar cells are concerned, I have shown you like the devices which were developed in our division only, actually in RC&D. Those devices, after 37 years of, you can say, life, they are still showing, and the degradation is less than 5%.
But they are under controlled environment.
They are under controlled environment.
Yes, but when I say I'm installing it in the rooftop, there is a lot of dust, a lot of rain, whatnot. Everything is accumulating on the surface. So that also will lead to some drop of efficiency for a period of time. So, and in the present scenario, it is difficult to clean them also. So how do we, I mean, what is the level of drop in efficiency? I know it is within the acceptable limits, but still, as a figurative thing, how much it would?
As far as the like device functioning is concerned, the efficiency will not fall because the rule, you can say there are only few things which affect the device efficiency. One is the temperature. When the temperature rises, you can say efficiency decreases. But there is no permanent damage, especially in silicon I'm talking, because of the rise of the temperature up to 80-70 degrees centigrade. Once it comes in the evening at the room temperature, less temperature, it actually adjusts for that. Next thing is that there is another problem, that is of the contacts. The contacts actually, these contacts goes bad over the period of time. That is the only issue, but that is not actually affecting the efficiency. That is affecting the collection efficiency, I would say. Efficiency of solar cell remains same. Third issue is of the dust issue. Dust issue is not a big issue in the household devices because one can go and clean these things. It is an issue on where you have make big, you can say plants like in Thar, you can like in desert area where it is very difficult to clean. So for that purpose, people do a coating of like super hydrophobic surfaces like PTFE and all those things. So then they wait for the rain. Rain comes at least once in a sometimes, and then once the rain comes, it will immediately wipe off entire dust in. Otherwise, cleaning, of course, as you said, is a very difficult. Cleaning is a big issue with this thing.
Okay.
And there is another issue regarding the bird. I heard something that it reflects light, so the birds which actually are you can say passing over the panels, they become blind, something like that. But there are other issues.
So one of the participants has asked the question: what is the scope of the research in this photovoltaic solar cells in the next decade?
There are a lot of scope. See, entire world is waiting for the. See, you want to replace the silicon because it's a very expensive. Now you are, as I said, there. I didn't go too much into those things. There are different possibilities. One is the perovskite solar cells. Another is polymer solar cells. Third is dye sensitized solar cells, and some other small countries. So right now there are open challenges are the stability issue and the efficiency issue. Efficiency is still lower, so you have to find out a suitable material which actually is not degradable. Whatever I have showed you, mostly the measurements has been done under a you can say under a controlled atmosphere. As soon as you remove those devices outside them, that actually they die within 2-3 days. So stability and efficiency, these two are open challenge, and all the like if you can, it's a totally good scope of research. You have infinite number of molecules, especially when you go for organic molecules, infinite number of semiconductors with small changes in the structure. You can change the properties, you can change the band gap, you can change all other things. So you have an infinite, you can say, opportunities. You can say sky is the only limit until someone find out a best possible working devices. Once that device is commercialized, then of course that will work.
See, there's a lot of scope from what we call it lab to land. Everywhere you have lot of opportunities in R&D as well as industrialization as well as commercialization, all these things. So solar is the buzzword now. Like many people said, after Y2K, software will die down, but software is still ruling the world. Similarly, now they're shifting towards the solar and renewable energies. So solar has got a lot of scope, and the students who are interested to pursue the R&D in solar related activities definitely will have very good opportunities to pursue their PhDs or careers.
Sure. This is correct. Because it's an open challenge, it's energy needs. As I said, if you can find out one pair of material which is stable, which is non-degradable, and then you can change everything. Actually, afterwards, then every you can say every building will have a you can put in the cloths also the solar cells. Every building have their own power plants. Right now, silicon is having it's expensive, and there are very other issues with the silicon like waste removal, all those things. There's several issues. Because of that, it is bulky. Also, putting there is also an issue. But once it will become like organic is commercialized, it will change the world.
It will come to a stage where you can paint your surfaces with this thing.
Yes.
Is there any more questions? So you can just leave your questions in the chat box. So thank you very much, sir, Dr. Anil Kumar Chauhan, sir. So now I'm requesting Srimati C.H. Kamlalakshmi madam for give a feedback about Dr. Anil Kumar Chauhan's presentations. So madam.
Good morning, one and all.
Thank you, Dr. Anil Kumar Chauhan, sir. Your talk on photovoltaic devices is very informative. Through your talk, starting from solar energy as a renewable and sustainable energy, its utilization as a solar cell, preparation of inorganic and organic solar cells, its working and the spectral distribution of the energy and different parameters involved is very clear and quite interesting. The insight you have given not only useful for the students, but also for the faculty and the research experts. And this was whatever the lecture you have given is very useful for further research studies, sir. Thank you very much. Thank you, sir.
Thank you, madam. Thank you.
So now I am requesting head of the department, Dr. T.K. Visweswara, sir, so to forward it to the vote of thanks to the Dr. K. Suresh, sir. Dr. K. Suresh, sir, I requesting you to give a vote of thanks.
Okay, thank
Am
you,
I
sir.
audible, sir?
Audible. Sir, sir.
Good.
How to stop sharing actually?
So the Department of Physics, Government College Autonomous Rajahmundry is very much thankful to the resource persons. Today's resource person, Dr. Sanjeev Kumar and Anil Kumar Chauhan, sir. So your explanation is extraordinary, and this is more useful for the student as well as teaching community. So the department has some gratitude towards you for wearing the time and spending a lot of time. And I must say thankful to V. Nataraju sir and Pant sir for providing this kind of opportunity to our department. Of in future, we will have much more webinars like this. Thank you, one and all. Thank you to the organizers. And I must, Dr. K. Suresh sir will give a vote of thanks. Thank you.
Thank you, sir. Respected dignitaries, invited speakers, organizing committee, and the participants, a very good afternoon to one and all. In view of National Science Day, the Department of Physics is organizing a series of events. I am fortunate enough to propose vote of thanks on behalf of Physics Department, Government College Autonomous Rajahmundry. In this view, I extend my gratitude to our Honorable Joint Director of CCE and Principal, and also President of today's webinar, Dr. R. David Kumar Garu, for gracing the event in spite of his busy schedule. And I also thank the in-charge principal and Vice President of today's webinar, Sri K. Anjaneyulu Garu, for his encouragement. A special thanks to our in-charge of Physics Department, Dr. T.K. Visweswara Garu, for arranging and providing immense support to make the webinar successful. I sincerely express gratitude to our resource persons, Dr. D. Sanjeev Kumar Garu, working as Assistant Professor of Physics in this college, and Dr. Anil Kumar Chauhan Garu, working as Scientific Officer G, BARC, Mumbai, for sharing knowledge by delivering clean, excellent, thought-provoking presentation. Thank you, sirs. I must thank the organizing team for working hard for the past few days to make this webinar successful. Finally, we thank all the participants for active participation to make it a grand success. Thank you, one and all.
Not this speaker is muted.
Thank you so much, sir.
Especially for the keynote speakers, spending for your valuable time. So making your time adjust and so available for us to your sharing your valuable knowledge. Especially for Dr. Anil Kumar Chauhan sir, even there is some like power so problems from your side, but last minute that you said that okay, it's now restored and so you are ready within 5 or 10 minutes. So we are very happy that sir. So we are thinking that it is not possible from your side, but finally it has happened to be successful. So we are very happy for that. So thank you very much, sir, for our very valuable and informative lecture. So thank you once again to all the participants and also I'm thanks to all our the committees of the organizing members for their relentless effort for making this successful. Thanks a lot.
Thank you for your nice words.
So the session will be closed so that